So last time we were working with quantifiers. Essentially, if we only use propositions with no variables involved, then we can't really say any interesting thing about mathematics. So we need to kind of strengthen our logical system, and to do that, we use quantifiers. And remember, quantifiers are one of two ways of making propositional functions into propositions. Does anyone remember the other way? For instance, how can I make p of x, which is this statement, x times, or x is greater than 0. How do I make this a proposition? What are the two different kinds of ways?
Provide a value for x.
Yes, I can either provide a value for x, or I can use a quantifier, right? So the two options are provide a value for x, such as -3 is greater than 0. Now this I can determine whether it's true or false. The other thing that I can do is I can provide a quantifier, like exists an x in a certain domain, such that x is greater than 0. Now, depending on the domain, this is also a proposition of a different kind than this proposition, and I can determine whether this is true or false. Right? Y'all with me?
Yep.
Great. Okay, so last time we went over the propositions for all. So for all x, p of x. Can someone tell me when this is true and when this is false? Where here I'll put x is inside a domain.
That's true when all x's in the domain are true, and false when
That's right. This is true when for every x in the domain, the property p of x holds, or p of x is true. And it's false when there exists some x in the domain such that p of x is not true for that x. We also talked about the existence quantifier. There exists an x such that p of x is in D. When is this proposition true and when is it false?
It's true when there's one or more values.
Exactly, when there are one or more values of the domain such that p of x is true. And it's false when
there's none.
When there are none, right? Or in a kind of leading question, having no x's in the domain such that p of x holds is the same thing as having for every x in the domain not p of x being true, right? Does that ring any bells?
Yes, it does.
Okay, good. The last one that we introduced was there exists a unique x such that p of x, such that x is in D, and this is just saying there exists a unique element such that p of x is satisfied. So my kind of leading questions were to present to you De Morgan's laws. This is the second iteration. So De Morgan's laws are going to tell us how to negate quantified propositions. So for instance, I want to negate the proposition for all x, p of x. So this proposition is true when P of x holds for all x, and it's false when there exists at least one x such that P of x doesn't hold. So what is a nice equivalence with this where I involve some not P of x? Remember, the original De Morgan's was something like this. If I want to negate P and Q, I want a statement involving the negation of P and the negation of Q. And it turns out that the way that we negated it was by having an OR. Here's our original De Morgan's. Now I'm saying I want an equivalent statement to, it is not the case that for all x, P of x, and I want it in the form of something involving not P of x. So what should go in front of the not P of x? So it's not quite there does not exist an x, it's that there does exist an x. Also nice, how did you get that reverse E into the chat? I don't know how to do that, that's cool. But the point is that this statement, something holds for every x. If I want to negate it, this is equivalent to P of x does not hold for every x, or there exists an x such that P of x does not hold, or there exists an x such that the negation of P of x holds. Are we okay why this is an equivalence, at least on the level of language?
Yes.
Any questions about this equivalence? Okay, so the other version of De Morgan's is the following. I want to negate the proposition there exists an x such that P of x holds. So this proposition, there exists an x such that P of x holds, is true whenever there exists an x in the domain such that P of x holds. And just in words, how do we make this proposition false? How do we negate it?
There are no x such that P of x holds.
Yeah, there are no x such that P of x holds, or for all x, what holds?
The negation of P of x.
Yeah, exactly. For all x, the negation of P of x holds. So this is very reminiscent of what we saw in the De Morgan's laws for just propositions, where you can distribute a negation to a bunch of propositions as long as you change the sign. We can do a very similar thing here. If we want to negate a for all quantifier, it changes to a there exists and the negation on the proposition. Similarly, if we want to negate there exists, you can kind of push the negation through. It becomes a for all and a negation of the proposition. Any questions on this? Notice what this implies. Let's assume that the domain is finite. So if the domain is finite, what's another way of writing for all x P of x?
P of x1 and P of x2.
Right, exactly. So if we assume the domain is finite, then the negation of for all x p of x can be written as the negation of p of x1 and p of xk. And then essentially what I'm showing here is that the negation of a big collection of ands is equivalent to not p of x1 or not p of x2 or not p of xn. But then if the domain is finite, does anyone remember what a whole bunch of ors mean? Or what a translation for a whole bunch of ors is?
There exists.
Exactly, there exists. So this is equivalent to there exists an x such that not p of x. So I'm just showing you this proposition, which we agree with, what it looks like if you assume your domain is finite, and then it looks like a generalization of De Morgan's that we already know, where if you want to negate an and statement, you negate all the propositions and all the ands become ors. So I'm just trying to make it very clear how this is trying to do exactly the same thing, just this holds in cases where your domain could possibly be infinite. Any questions here? No? Everyone's happy? Okay. Let's do an exercise. So let's try to write out propositions associated to the things that I write. So let's assume that the domain is all people. And let's see. We should just assign different propositions as they come up. So let's try to write out the following. Everyone in your class in 381, in this 381 class, has a cell phone. Okay, so we need two propositions, right? We need one propositional function which determines whether or not you're inside the class, and we need one propositional function which pertains to owning a cell phone, right? And then this is saying, yeah, and so the domain is all people. So what should we do for this? How should we translate this into propositional variables? Well, I should start off with for all. There exists won't work because I'm trying to say something about all students in my class. So for all x, but here, this for all x is actually talking about all people. So what should I do here? Right, so I definitely need something about being in the class. So let's say CLX is the proposition X is in the 381 class, and P of X means X has a cell phone. So right, this is already holding for all X in the domain. Let me perhaps just write out this first one, and then we can discuss. So I would translate this proposition, everyone in the 381 class has a cell phone, as for all people, if the person is in my class, CLX implies P of X. Right. For all people, if they're a 381 student, they own a cell phone, is a way of saying everyone in the 381 class has a cell phone. So for all X, if they're in my class, then they have a cell phone. That's an excellent question. Why is it not and? So why not for all X, CLX and PX? So this is incorrect for translating this proposition, because if I have this proposition for all X, CLX, and P of X, then I can actually, this is equivalent to saying that everyone is in my class. Every person in the world is in my class, and every person in the world has a cell phone. But this doesn't need to be true when this is true. Everyone in my 381 class has a cell phone could be true when everyone not in the class doesn't have a cell phone, and when there exist people not in my class. But this proposition is only true if everyone in the world is in my class and everyone in the world has a cell phone. Does that make it clear why this is the correct translation and not this? Yeah, great. Let's do another one. Let's translate the phrase someone in the class has seen a foreign movie. Well, I don't think I would use a there exists a unique here, because I'm not preventing more than one person from having seen a foreign movie. I'm just asserting the existence of someone who has seen a foreign movie. So let's see. Here I would put there exists an X such that this person is in my class and they have watched a foreign movie, and f of x. So let's consider if this is possibly the same as being in my class implies that they have watched a foreign film, right? So let's write it out this way. So my proposition for how I'd write this is there exists an X such that X is in my class and X has watched a foreign film. Are there other considerations that we should make? For instance, is this equivalent to there exists an X such that if they're in my class, then they have watched a foreign film? I don't think that this is correct, because this statement would be true if there was no one in my class, right? An implication is always true when the premise is false. So this statement would be true if there was no one in my class at all, right? Because then there would just not exist anyone in the class, so an implication statement would be true. Whereas this statement both says there is someone in my class and they have watched a foreign film. Does this clear up why this one works for this proposition and not this one? Yeah, so we're starting to get into some kind of tricky propositions. So the moment that we start doing quantifiers, and especially when we start doing nested quantifiers, it takes a little time to go through and figure out precisely what each proposition means and when it's true or false, right? This just says there exists a person in the world such that if they are in my class, then they have watched a movie. This is close to this one, but this would be true when no one is in my class, and this requires someone to be in my class to be true. Someone in my class has watched a movie. Such a person exists. Okay, let's do another one. Let's kind of go. Let's do the following example. Let's negate the following thing. I want to negate the proposition for all x, p of x implies q of x. Let's see. What should we, just for fun, I'm going to say the domain is people, and p of x means x has been born, or x is born, and q of x is x will die or has died, one or the other. So then just in words, what does this proposition translate to in words? Right. If I leave out the negation, then this proposition is, for all people, if the person is born, then they will die. And the negation is, it is not the case that for all people, if they are born, then they will die. Exactly. So let's use De Morgan's to find an equivalent proposition. So what does De Morgan's tell me that I can do if I have a negation in front of a for all symbol?
Turn it into there exists an x and then negate the.
That's right. Yeah, I think of De Morgan's now as pushing an x through a quantifier and changing the quantifier. So I get there exists x such that it is not the case that p of x implies q of x. And I want to go further, actually. Yes, all of your comments are correct. I want to go further. So this is still true. This proposition is equivalent to this proposition. But in this case, so this proposition is there exists a person such that it is not the case that that person is born implies that they will die. What I want to do is I want to go further and negate this proposition. I want to end up with a negation only in front of the atomic propositions. So how can I go about negating an implication?
Can we still go ahead and use the substitution, the implication substitution first?
Yeah, exactly. So the contrapositive is a way of producing an equivalent proposition to this one, but it's not exactly the same as negating. So here's an important point that I want to point out. The proposition P of x implies Q of x, the contrapositive is not Q of x implies not P of x. But these are equivalent, right? Whereas the negation is going to produce a proposition which is not equivalent. In fact, it's somehow the reverse of equivalent. Yes, here I want to do implication substitution and then De Morgan's again. So here, this is equivalent to there exists an X such that negation, and the implication substitution here is not P of X or Q of X. And now I can use actual De Morgan's. Sorry, my paper's crooked. This will be, there exists an X such that, and then De Morgan's here after a double negation will be P of X and not Q of X. So here is kind of like the most basic that I can do, because, and this will be something that I ask of you on your exams, I'll ask, find an equivalent statement to a given proposition such that negations are only on elementary or atomic propositions. So can someone translate into words what this proposition reads as?
If there exists somebody who will be born and not die.
Right, yeah, right. There exists a person who is born and who will not die. Right, that's equivalent to, it is not the case that for all people, if they are born, then they will die. Okay, any questions about this? Oh, I hear there's a question, but I cannot hear you at all. I still can barely hear you. Okay, sounds good. While you type, I might do the following fun example from Lewis Carroll. And then I'll get to your question. So in this example, I want for us to kind of approach an argument using quantifiers and propositional variables. So I'm going to let the domain be all people. And then I'm going to take the following propositions. B of X is a baby. And L of X is logical. And M of X is X is able to manage a crocodile. And then D of X is despised. Okay, so here is a argument that Lewis Carroll wrote. So what I would like for us to do is work out an example. So as a first proposition, we should write babies are illogical. How would I write babies are illogical? There's a question. So if, for example, you had someone in class has a cell phone, if you were told to translate that sentence into math, we could come up with our own domains. Yes. So you bring up a very good point that domain, like changing the domain, has a big impact on how you write the proposition. So if the question is there exists a student in class who has a cell phone and the domain is students in class, then it's just exists X such that P of X, right? So in that case, it's a very simple proposition. Whereas if it's the proposition, there exists a student in my class who has a cell phone where the domain is all people, then you need to do the more complicated proposition where you have an implication. Or, yeah. Does that help? Yeah, and on an exam, I would try to specify which domain you should use. And then if I don't specify which domain you should use, and you pick a domain which makes the problem easier, then good on you. You win. Can't take points off for that. Okay, how do I write babies are illogical in math? Yeah, exactly. For all x, x being a baby implies x is not logical. Very good. So using a quantifier, for all x, b of x implies not L of x. Do we agree? Do we agree that I shouldn't have an and statement here? Because if I had an and statement, then that would say that everyone is a baby, at the very least. And everyone is illogical, which is not equivalent to the statement babies are illogical. Okay, the next proposition, nobody is despised who can manage a crocodile. How would I translate this into propositional variables? It's written kind of backwards, but what this is really saying is that if you can manage a crocodile, then what?
So would we use here the
Then you're not
negation of there
despised.
exists? Okay,
Here I would once again use a for all, because this is saying that if you can manage a crocodile, then you are not despised. Exactly. Yeah. Thank you, Alyssa. So for all x, if you can manage a crocodile, then you won't be despised. Any questions on this one? Ah, and also Mahita, thank you. No, there are two more. So the next one is illogical persons are despised. Can you write it as the negation of for all x, if you manage a crocodile, you are despised? Let me think about that. So you're saying it is not the case that for all x, if you manage a crocodile, then you are despised? No, here, the negation of this proposition is probably there exists a person who can manage a crocodile and is not despised. But this is saying everyone who can manage a crocodile is not despised. So for instance, this one gives you a surefire way to stop being hated. You just learn how to manage crocodiles. Whereas this one says, there's no guarantee. Sorry, you can't see what I wrote up here. Right. Okay, so how do we write illogical persons are despised? Yep, for all x, if you're not logical, then you're despised. And then the conclusion of this argument is the proposition, babies cannot manage crocodiles. And how do I write that?
For all x, b of x implies not m of x.
Exactly. If you're a baby, then you can't manage a crocodile. Very good. And it turns out that, so remember in chapter 1.6, we started analyzing arguments, but we didn't have propositional variables. It turns out when we return to section 6, we will start analyzing arguments such as this one, and we can conclude the nice fact. And indeed, it'll turn out that this is a valid argument. So from the statements, babies are not logical people are despised, and if you can manage a crocodile, you are not despised, we can indeed conclude that babies cannot manage crocodiles. And also that babies are despised. Yes, it also implies that babies are despised, correct. Any questions about this collection of translations of propositions? No? Everyone's happy with what we've done here? Well, that's great news. Let's move into a more challenging section, which is section 1.5. So section 1.4 was all about introducing these quantifiers and how to negate. Exactly, we just modus ponens and modus tollens a baby. Great. So we're going to get into 1.5, which is when we start nesting quantifiers. So before we get into it, are there any questions? No? Okay, let's go. So nested quantifiers. Here, I want to start writing out a couple examples. What do we make of a proposition like, for all x, there exists a y such that x plus y is equal to pi? Right? So here, I'm starting to kind of add more variables and add more quantifiers into the mix. So I know that I kind of just said it, but can someone talk to me a little bit about what this proposition is asserting?
So for all x's, there is a y, there exists a y such that x plus y equals pi.
Right. So you can kind of think about going through it in order. So the first thing says, pick any x from the domain. Let's say the domain for x and y are in the real numbers. So this is saying, pick any real number, then you can find a second real number such that their sum is equal to pi, right? Is this proposition true? For x and y in the real numbers? Yeah, this is true. Because if I pick any real number x, then I can always pick for y the number negative x plus pi, right? if I pick x is equal to 5, then I can pick y is equal to -5 plus pi. And look, boom, 5 plus -5 plus pi is equal to pi, so I'm good. And I can do this for any x. But notice I'll have to pick different y's each time, because if x is equal to e, then y has to be equal to -e plus pi. So this says, if I pick any x, then I can find some y such that this proposition holds. So this is true. By the way, is this true in the integers? If x and y are integers? Nope, that's false. You can't add integers and get pi. Okay, here's another question. There exists an x such that for all y, x plus y is equal to pi. What's this proposition saying? Let's say, once again, x and y are in R. So once again, if you're kind of going through it, you're saying there exists an x such that for all y, x plus y is equal to pi. So this is the way that I read through these. I say the first one. For all x, there exists a y. And then here I read, there exists an x such that for all y, such and such things hold. Is this proposition true? Does there exist a real number such that for any other real number you pick, x plus y is pi? Right, this one's false. Here, this is saying for any number you pick, you can pick another thing such that this thing works. This one is saying there is one x such that this always works for any second choice, right? Let's do some more examples of some of these nested quantifiers. So here are perhaps here's an easy one. If we do nested quantifiers, but they're both for all. So for instance, for all x and for all y, x plus y is equal to y plus x. So here, when I'm doing for all and a for all, when I'm nesting these, you wouldn't be allowed to use y in your definition for x, right? So you're asking about this problem here, right? Where I'm saying for this one. So I'm not actually proving what's going on, but the idea is that for any x that you pick, you can find a y such that this proposition is true. And if you want to explicitly pin down how to describe that y, it does involve x. There's not an issue with what I have written here. Is that okay? For the one under it, you wouldn't be allowed to use y in your definition for x. So that's correct. Here, this is saying you have to be able, like, for this proposition to be true, you have to be able to pick an x such that for any y real number that I then pick, the sum is equal to pi. But there's no x such that when you add any real number to that x, you get pi, right? Yeah. Okay, so the easy ones are for all x and for all y proposition. So maybe I should write for all x and for all y, p of xy. So this is the assertion that for any, so this is true when for any values x and y, p of xy is true. And here's an example of some such proposition. For all x and for all y, x plus y is equal to y plus x, right? This proposition is true if we're working with, say, the integers or the real numbers or the complexes or whatever. So when is a for all x for all y, p of x, y false? This is saying for any pair xy, p of xy is true.
So it's false whenever, oh, sorry. Whenever any value of x or y makes p of y false, or p of xy false.
Right, it's false when there exists a pair. Say A, B, where this is A is an element of the domain of X and B is an element of the domain of Y, such that P of AB is false. Right. We okay with my description of this nested quantifier? Yeah, all you need is the existence of one pair of elements such that the proposition is false on that pair. Okay, the other easy one, oh man, it's almost out of time, shoot. The other easy one is there exists and there exists. So there exists an x, there exists a y, such that p of xy. And this is true, well, when there exists a pair xy such that p of xy is true. And when is this false?
When there is no pair of xy that makes that.
Yeah, it's false when there is no pair xy such that p of xy is true. Or another way to say this is that it's false when for all pairs not p of xy. Yeah, very good. And it's already 10:08, and since it's Friday, I'll let y'all off 2 minutes early. Have a lovely weekend and stay safe. And we'll get back on Monday with more nested quantifiers.
Thank you.
Thank you. Have a great
Janae, let me write you an email back. So yes.
I have a question on the assignment 3 homework.
Sure.
So is this homework just on 1.4 or will you add more questions on?
I will add more questions. So I'll add questions today and I'll add questions on Monday.
Okay, got it. Thanks.
Yep. Angel, any questions?
I'm just finishing writing.
Oh yeah, sure. Take your time. Anything that I can help with?
Kinda. I don't really understand the format, like
Okay.
how it's in an ordered pair.
So would examples help?
Yeah. I think.
So let's think about some proposition. There exists an x, there exists a y, such that what do I want to put here?
Move down the paper a bit.
Oh yeah, sure. such that x times y is equal to 1. So this probably isn't, I'm trying to think of one that'll kind of correctly illustrate what's going on here. But are you okay with like reading out what this statement says?
Yeah,
So is this a true statement or a false statement?
that would be true.
Right, it depends on the domain, but
Or
right,
yeah,
right.
it's just integers and it's true. If it's not, then it's false.
Right, exactly. Here's one. Exists in x and exists to y such that x plus y is equal to 0 or is equal to -1 when x and y are in z plus. Is this true or false?
I don't know what z plus means.
This is, let me write integers that are greater than 0, greater than or equal to 0.
And that's going to be false.
That's going to be false because there's no pair of integers where each of those integers is greater than or equal to 0 such that they add to -1.
Okay.
Right, so
then-
I know that this is false because no such pair exists.
Okay. All right. I think I got it.
Right, whereas if I had, let's just do a couple more examples. There exists x such that for all y, x plus y is equal to 0, and let's once again have x and y in z greater than or equal to 0. I know that I didn't go over these, but this will probably help. So what is this statement?
There exists an x for all y such that x plus y equals 0.
Right, and where this is the domain. Is this statement true or false?
That is that greater than and equal?
So this is saying I'm taking from integers which are either 0 or greater than 0,
Oh.
and I'm saying that their sum is equal to 0.
Then false?
Yeah, this is false. Why is this false?
Because x x basically has to be 0, or y can be anything, but x has to be 0.
It's something like that. For
Yeah.
any x that you pick, you can always pick a y greater than 0 such that their sum is greater than 0, right?
Yeah.
So it's never possible to find a single x that will work for all y's.
Okay.
Now let's change it around a little bit. Now, well, here I could even remove the greater than or equal to 0 thing here, right? Does there exist an x such that for all y, x plus y is equal to 0? Is this, now that I've changed this, is this true or false?
Still false, right?
Exactly, it's still false. What if I change things to for all x, there exists a y such that x plus y is equal to 0 for x and y in z?
Still false.
This one is finally true because this says pick an x, then I can find a y such that their sum is 0.
Okay.
Here, there has to be one x which works for every y, but here, for every y, I have to be able to pick an x.
Okay, so it matters like the order they go in.
Definitely matters the order in which they go
Okay.
in. It doesn't matter for these two. For all, if it's for all x, for all y, and exists x, exists y, then order doesn't matter. It turns out that you're just talking about whether or not there exists a pair where something is true or false. But for these, it does matter the order, definitely.
Okay. Right. Then I think I'm pretty comfortable now.
Great, yeah, more examples help a lot.
Yeah. All right. Thank you.
I'll do these examples again on Monday, so you'll be bored.
All right. Thank you. Have a
All
good
right,
one.
you too. Bye.